Hello, this is Mr. Craig, and this is quiz number 2 for period number 7. Questions 1 through 4. Refer the following gases. Select one lettered choice that best fits each statement. A choice may be used once, more than once, or not at all. Alright, so number 1 said, would cause a solution to become more basic when placed in water. Well, make sure that we can recognize a certain type of weak base, because it's commonly asked. Hopefully you wouldn't say the nitric acid, because hopefully you recognize that that's a strong acid. So therefore, hopefully you know that ammonia is the weak base. Therefore, when ammonia is placed in water, NH3 is placed in water, you need to ask yourself, well, what is that weak base going to do? Well, it's going to rip a hydrogen off, and it will form NH4, which is a conjugate of the ammonia, which is a weak acid, and hydroxide. So there is our answer for number 1. Number 2 has the weakest attractive forces between particles. So let's see here, weakest attractive forces between particles. So we're looking for the intermolecular forces, or the, well, I like the question, weakest attractive forces. So typically when we do that, we want to look at something that is a nonpolar compound, because those have dispersion forces. And when we look at SO3, SO3 has dispersion forces, and we have it with a double bond, a single bond, and another single bond. So we have 8 electrons there. Ammonia, well, that one's out because that actually is a polar compound, and also, since it is a polar compound, we have a NOF situation, which is a hydrogen bond. So that's really strong bonds. We have another situation that could potentially be hydrogen bonding. So now we're down to these 2 noble gases. And noble gases typically have the weakest intermolecular forces, or weakest attractive forces, as this question states. So now what we need to look at is which one of these noble gases weighs the less. And in this case, helium would be our victor. So the weakest attractive forces should be helium. Okay, and again, as I stated on the memo here, radon is very massive and actually forms quite a few compounds, so it does have a little bit stronger forces there. And helium will never form a compound. Alright, number 3 has the slowest average atomic or molecular speed at 1 atmosphere and 273 Kelvin. And again, realize that these are all gases. So even though you do not have this equation where we have the root mean square speed, and you don't have to memorize this, 3RT over big M. The temperature is the same for all of these. The R is the same for all of these. And 3 is 3. So what is the defining factor here? This big M. Whenever we're talking about gases, what does big M represent? Hopefully you recognize that that represents molar mass. Now, you don't even need to know this equation to be able to answer the question. Hopefully you recall that when we look at gases, those who are light in mass move very, very quickly. Those who are massive in mass move very, very slowly. So the one that we're looking for is the most massive, so we're looking for the slowest average atomic speed or molecular speed. So whichever one weighs the most. Well, sulfur is 32, and oxygen is 3 times 16, which is, I think, 48-ish. So that's roughly, what, 70, 80? We'll say 80, just for kicks and giggles. Well, helium's out. That's really fast. Ammonia's out because that's around 18 or 17. We've got 3 oxygens, a nitrogen. That one's less. So now it's down between radon and sulfur trioxide. Well, I don't have the molar mass of radon memorized, but it does have a molar mass of around 222. That's pretty significant. So the more massive one is easily the radon here. So number 3, I think it was, yeah, should be radon, which is, again, the most massive, E. Alright, number 4 has a rate of effusion from a pinhole closest to that of krypton when the temperature is the same. So when we do that, now what we need to look at for rate of effusion, we need to find something that is a similar mass as krypton. And krypton has a molar mass of around 83.8. And of course I just erased all those molar masses that I just worked out. 83. I think it was... Here, now, let me go see if I can back it up. See if I've got it still on there. Yeah, there we go. So it had a molar mass of around 80. So I'm going to say A, which is closest, because I know that the hydrogen here, that's 48, but 15 is not close enough. So I'm going to say A for this one as my educated guess, and it's closest to. I don't think there'll be another answer that's closer than 80. So A should be the correct answer for 4. And again, it's all dependent on the mass. So equal masses, those particles move at the same speed. Alright, number 5. Which of the following groups contains only atoms that are paramagnetic in their ground state? Now, paramagnetic means that if I'm looking at electron configurations, say like, say 2s, okay, and 2p, let's just say for like oxygen. 1, 2, 3, I believe that's right. Oxygen has, nope, one more, sorry. So there's oxygen's electron configuration, just for kicks and giggles here. So what paramagnetic means is that we do not have all the orbitals that occupy electrons have to be, or are not paired up. Diamagnetic means that all the electrons that have all the orbitals that have electrons are paired up. So what we need to do is look at the periodic table. Get my mouse to work here. So, whoops, we got to go back and forth. So we've got beryllium, oxygen, and the group's only atoms that are paramagnetic. Well, I know beryllium is in group right here, number 4. So that one's definitely out. So A is out. Magnesium is also in group 2, so that one's out. Potassium looks good. Yeah, here we go. C. C's the best answer. Now, just real quickly, yeah, krypton and zinc. Good. So C, letter C. Okay. All right. Number 6. Noble gases are, and this feels like a rerun. Noble gases are highly reactive with many elements. Absolutely not. Non-reactive with many elements. Well, has to be that. Also, we know lithium is not, bromine is not. Okay, so letter C. Make sure that we know the 4 groups. So group 1A, actually let me go to the periodic table. Group 1A, that has hydrogen, lithium, sodium, and all these guys. Alkali metals. Group 2A, that has beryllium, magnesium, calcium. These are alkali earth. Jump all the way over to number 7, where we have fluorine. Fluorine, chlorine, bromine, iodine. Whoops, come back. These guys all are group 7A, are halogens. And then this very last column here that starts off with helium at the top, which you may not be able to see, is the noble gases. So make sure that you know those 4 column names. Alright. So again, letter C is the best answer for number 6. Number 7, what is the oxidation number of oxygen? And again, oxidation numbers deal with the potential charge that an element may have. So here we have what's called hydrogen peroxide. Now, again, we don't care about the hydrogen name, but the peroxide should mean something to you. Back when we were doing polyatomic ions, if I had something like perchlorate, okay, perchlorate, if I could spell perchlorate, chlorate itself is just ClO3 with a -1 charge. Perchlorate means that I have 1 more oxygen, but my charge remains the same. Same thing's going on here with the oxygen. Oxygen by itself has a -2 charge. The peroxide now means that I have 2 oxygens with a -2 charge. I'm adding an oxygen while maintaining the same charge. Also, we know that the oxygen has a total charge of +2 because we only have 2 hydrogens, which have a +1 charge. There's no way that a hydrogen can have more than a +1 charge. Plus charges originate from the nucleus, and the nucleus for a hydrogen atom only has one electron. So the best choice for this answer is letter B. Yes, oftentimes oxygen will have a -2 charge unless it's in a situation where we call it a peroxide. This is the only time that I know that oxygen has a -1 charge. Alright. Number 8. Which compound is amphoteric? Make sure that we know what the term amphoteric means. Amphoteric means that this thing can behave as an acid or as a base. Now, one of the criteria for something to act like an acid, it has to have a hydrogen. That one's out. That one's out. Okay. A criteria for something that behaves like a base doesn't necessarily mean that it has to have a hydroxide. Don't think that way. However, it must be able to accept an additional hydrogen. Well, phosphoric acid isn't going to gain any more hydrogen atoms because phosphate has a -3 charge. So we have the 3 hydrogens there. Same thing with the ammonium. Ammonium only has room for one more hydrogen. I'm sorry, ammonia only has room for one more hydrogen. Ammonium cannot take on any additional hydrogens. Remember, the special exception or the special rules for carbon, nitrogen, oxygen, fluorine, that these guys can only obey an octet rule. They cannot have more than 8 electrons. Therefore, that one's out. Well, by process of elimination, that's our only one. Now, as a heads up, when we look at amphoteric substances, oftentimes these things have a charge. Also, they have room for another charge. So, now even though the ammonium has a +1 charge, we can't add any more hydrogens to this one. However, bisulfate, HSO4 with a -1 charge, we can stick another hydrogen on there to make sulfuric acid. Or we could remove another hydrogen from this and make just sulfate ion. So these, whether I add a hydrogen or I lose a hydrogen, okay, these are my 2 substances or 2 choices. Hopefully I'll give you some more of those here. Number 9. To identify an unknown metal sample, the density of a metal was determined in a laboratory. The density was determined to be 19.32 grams per milliliter. If the volume of the sample was determined to be 0.01 liters, what is the mass of the sample? Well, here we go. We have, if we know the volume and the density, start off with the volume. So you have this, liters. Since this is in milliliters, we have to change this to milliliters. So there's 1,000 milliliters in a liter. And we have 19.32 grams per milliliter. Alright, so 1,000 times 0.01, that equals 10 milliliters. Okay, so 10 milliliters, 19.32 divided by that milliliter. Well, 10 times 19.32. Hopefully you can do that do that math in your head. So, best answer, B as in boy. Now that didn't take too much time and work. Okay, but you should be able to do that type of math with no problem. And yes, you will be expected to do that type of math on the AP exam. Alright, number 10. Consider the 3 sealed identical flasks represented below, each containing 0.1 moles of a gas, specified at 1 atmosphere and the same temperature, 273 Kelvin. So, in flask A, we have 0.1 mole of hydrogen. Flask B, we have 0.1 mole of carbon dioxide. Flask C, we have 0.1 mole of neon. Okay, let's get back here. So, let's erase those. Now, the mass of the contents in flask B is the greatest. Well, hydrogen will have a molar mass of around 2. Neon has a molar mass of around, I think, 20. Let me double check that. Neon, yeah, about 20. 20.18. So, 1 mole of that. So, 20 grams. And carbon dioxide is around 44. So, that one's true. That one's good. Number 2, the number of particles in each flask is the same. Well, if we have the same number of moles and the temperature is the same, I guarantee you the pressure will be the same, and the volume of this thing is the same as well, since we had the same moles. So yeah, it's good. The density of the contents in each flask is the same. Well, if we know the volumes are the same for each of these, and we have different masses, there's no way the densities could be the same. So only 1 and 2 are correct here. So letter C. Nope, make sure you know your gas laws, as I stated on there. Number 11. A reaction has a delta H value that's greater than 0, which means it's positive, and a delta G value that's greater than 0, which means it's also positive, at 25 degrees. This reaction is at equilibrium. This reaction, we don't know if it's at equilibrium, so we can't choose that. Could not be spontaneous at any temperature. Could not be spontaneous. That's true. Or I'm sorry. Could not be spontaneous. Could not be spontaneous at any temperature. Okay. When and will it be spontaneous? Actually, it'll only be spontaneous. Well, let's see. When hopefully delta S. Okay, we don't know anything about delta S, but we do have the positive. Right, that one's not correct. Could not be spontaneous at any temperature. It could be spontaneous at some temperatures. Could be spontaneous at a temperature above 25. If we increase the temperature, that might be good. I'll give that a somewhat of an okay. Could be spontaneous at temperatures below. Not gonna like that one, because if the temperatures are low, that's going to cause delta H to overpower the value of delta G. So we don't want to do that. Is at equilibrium at any temperature. All right. My best choice here is C. Now, here's our scenario. We know that delta G is equal to delta H minus T delta S. Okay. We don't know anything about the back part of this equation. All we know is that this is positive and this is positive. So what this is saying is part C could not be spontaneous at any temperature. Well, we do know part B I was hesitating for a little while. If this temperature is high enough, I could get the back part of this equation. If delta S has a positive value, I could get delta G to be spontaneous or be a negative value. So the way I would do that is make sure that my temperature is high enough. So not knowing what delta S is, the key here is could be spontaneous at temperatures higher than 25. So C would be the best choice for this very bizarre question. Okay. All right, number 12. Which changes are accompanied by an increase in entropy of the system? All right, conversion of O2 to O3. Okay, and even though you may or may not know this, we take oxygen gas plus an oxygen atom to make ozone. Okay, that's what happens up in the atmosphere. Or to go in the opposite direction, when ultraviolet light hits ozone, it breaks down into O2 and oxygen. All right, so let's see here. So that is a decrease. That one's out. Freezing of water is not an increase. It's actually a decrease. It's becoming more ordered. Sublimation of iodine. What does sublimation mean? It goes from a gas. I'm sorry. Strike that. Goes from a solid to a gas. Okay. So when we go from a solid, we're going from a very ordered state to a gas. So unfortunately, 3 can only be our choice. Okay. All right. Number 13. Which gas is least suitable for collection over water if bubbled through the water? Similar to the electrolysis demo that I did in class a couple weeks ago when I was talking about electrolysis. All right. What this question is asking is, if you are planning on collecting a gas because you're reacting it somehow, some way, one of the better ways, so you can measure pressure, so you can measure volume, is to bubble it through, kind of like our butane lighter lab that we did in General Chem. So we'll bubble the gas through the liquid. Actually, let me scoot this up. Remember in the butane lighter lab, where we had our trough of water and then we had our container, actually graduated cylinder. We then placed our butane lighter here, and this was full of water when we first started, and then the butane rose to the top of the graduated cylinder. Over a period of time, what happened was the water level started to drop because we had all this gas starting to be formed. So butane was being used in this case. Eventually we allowed for the water level, move the butane out of the way, we allowed for the water level to become equal with the water level outside as it was inside. Now that was kind of significant, a significant reference point. If we know that the pressure outside is equal to the atmosphere, we can also determine what the pressure of the gas is inside, in this case the butane. That's why we wanted to make the water levels inside and outside the same, so that we could make these gases the same pressure. Now, what we did not use was a gas that was polar. Why would you not use a gas that was polar? Well, back in solubility, just about a week or so ago, when we were talking about solubility rules and solubility with colligative properties, if you have a polar compound, it will dissolve within the water itself. It won't bubble right on through. Butane, which is a nonpolar substance, moves right through the water. Those water molecules are not affecting that gas, so that gas moves easily through the water. So what this is asking is, which of these is least suitable? In other words, all the other ones should be very good. Argon, is that a polar or nonpolar compound or substance? In this case, it's nonpolar. It's argon gas. Oxygen, also nonpolar. Carbon dioxide, also nonpolar. And again, if you need to draw it, everybody should know carbon dioxide has a linear shape. Oxygen has a linear shape with only 2 atoms, and argon doesn't have anything. So we know that those are out. However, ammonia, which is dissolved in a lot of our cleaners, is very polar. So if I try to bubble ammonia through water, I'm not going to see any gas produced. All I'm going to get is some smelly water. Okay? So the one that is least suitable, not soluble, least suitable for the collection over water, okay, is ammonia. Letter D. 14. Which classifies all the bonds in a molecule of propanone? And here we have the compound, and again, write it in the order that you see it. So we have carbon with 3 hydrogens. Then we have another carbon, and it has a oxygen. So actually we get it out of the way, and then carbon with 3 more hydrogens. Okay. Alright, and again, can't draw the structure. So if you ever see this in the middle, it really looks like that. Okay, so questions wanting to know about sigma and pi bonds. And again, remember, a sigma bond represents a single bond, a sigma pi represents a double bond, and a sigma pi pi represents a triple bond. So whenever we do something like this, if we were looking at a triple bond, we'd have 1 sigma bond and 2 pi bonds within that structure. So what we need to look at, let me erase that because that's actually a little boo-boo mark. So we have 1, 2, 3, 4, 5, 6, 7, 8 single bonds plus 1 double bond, which means we have 9 sigma bonds. And then since we have a double bond, we have a sigma and a pi, we have 1 pi bond. D's our best choice. You will see a question like this on Monday, I promise. Maybe not with this same compound, but very, very similar. Alright, number 15. Oh, I like this question. The symbols, where we have hydrogen with 1 neutron, molar mass of 1, which means it has 1 proton, where here it has a molar mass of 2 with 1 proton, which means it has 1 neutron in there. And then hydrogen 3, which has 2 neutrons, yet still the 1 proton. So we have different numbers of neutrons. We have different numbers of neutrons. What are you looking at? Isotope. Okay. All the others are organic definitions more than anything else. And if you're curious, here they are. And I'll let you pause it and read over it. If you want to learn these, that's fine. When you take organic chemistry next year, or whenever you take organic chemistry, you'll learn these, I promise. Don't get hung up over learning organic stuff. Trust me. Again, the material that we cover in this class covers 95 to 97% of the material that you will see on the AP exam. Organic chemistry is not worth spending your time over for maybe 3 or 4 questions. And trust me, if you get a 3 or you miss getting a 3, it's not because you didn't know those 3 organic questions. Alright. Number 16. Which applies to a 1 mole solution. Now mole means molarity. Okay. 1 mole solution of sodium chloride in water. Now again, sodium chloride, is that soluble or not soluble? Very soluble. Okay. Excuse me. Okay. Sodium chloride dissociates 100%. Okay. Alright. Now, adding sodium chloride lowers the freezing point. Well, yes. And make sure that you know what the Van Hoff factor is for this. So again, the equation, even though you're not doing the equation, you have this, okay, for lowering the freezing point. M represents molality, Kf is your constant for the freezing point depression, and I is your Van Hoff factor, which in this case is 2, because we have 2 particles that are dissociated from that 1 molecule. So yes, that one is true. Number 2, adding sodium chloride decreases the vapor pressure. Well, when we talk about vapor pressure is when a liquid changes into a gas. Okay? And the stronger the intermolecular forces, or the greater the external pressure. So if we have a strong atmospheric pressure pushing down on this liquid, we're going to reduce the vapor pressure. Or if the intermolecular forces are strong enough, we will reduce the vapor pressure. Or if we are able to elevate the temperature in which the substance boils at. So by adding sodium chloride, remember what I just talked about with the boiling point, or I'm sorry, the freezing point depression, we have another calculation for boiling point elevation. If the boiling point goes up, the vapor pressure goes down. Okay? Now again, we're saying it's the same temperature, but if the boiling point for a substance goes up, the availability or the ease for this liquid to change into a gas has been reduced. Okay? We are making it harder. We are actually helping the intermolecular forces by adding stuff in there, because now we're causing the boiling point to be elevated. Also, when we talk about external pressure, again, that all deals with the Van Hoff factor that we just erased. So this one's looking good, but I do want to talk about if I increase the atmospheric pressure, what is happening to the vapor pressure? Well, if I increase the atmospheric pressure, I'm pushing down on here, and I'm making the intermolecular forces much, much stronger, which means that the vapor pressure will go down. So it's an inverse proportionality. If the atmospheric pressure goes up or external pressure goes up, then the vapor pressure goes down. If the boiling point goes up, the vapor pressure goes down. We can reverse that. If the boiling point is reduced, because I removed some of the external pressure, the vapor pressure is now going to go up. Alright, and number 3, so we know that 1 and 2 look good. Number 3, adding sodium chloride increases, I'm sorry, I think that says decreases. Yeah, decreases the density of a solution. Well, we know that to be absolutely wrong. So our choices are 1 and 2, which is C. Number 17, how many total orbitals in a neutral ground state oxygen atom are completely filled? Well, probably the first thing we should do is write the electron configuration. So oxygen, we have 1s, 1 electron, 2 in there, 2s, 1 electron, another one, 2p. How many orbitals are there? 1, 2, 3. So we'll drop 1 electron in each orbital, and then we go back and double up. Now, a lot of people miss this question. on the quiz. I don't want you to make the same mistake on the AP exam. There's one orbital. There's another orbital. How many orbitals are in the p orbitals? There are 3. The best answer is letter C. Okay? We're not talking about filling up the complete p orbitals, but each one of those has it. Remember, when we talk about an orbital is a region of space where we're likely to find an electron. The maximum number of electrons that can occupy any one orbital is 2. I think if you remember that definition, this becomes a very, very simple question. Remember, no more than 2 electrons can occupy any one orbital. Doesn't matter if I have a d orbital that has 5 of those in there. Okay? To be completely filled, you've got to have them all in there. Now, also don't say, oh, wait a minute. If I took this one electron out and I put it right there, now I've got 4 orbitals that are filled up. Don't forget, when we talk about Hund's principle, we drop 1 electron in each orbital, then we go back and double up for a particular type. So that would not be the case. All right. 18. Calculate the delta S at 30 degrees for the reaction shown below. All right, so we have a delta G value, we have a delta H value, and we have some really phenomenal numbers. Now, what you may start doing is this. You might start writing down and going, okay, well, this is the equation we're going to use. But that's all I want you to write. Here's what I want you to do. This is an amazing question. And the first time I read it, I actually laughed. I really did. I laughed. I go, this is brilliant. This is not meant for you to actually do the calculation. You can't do a calculation without a calculator. This is a concept question. The concept here is not for you to calculate, but to recognize. Alright, so when we look at delta G and delta H, we know that it has a negative value. We know that it's spontaneous. Okay? However, we don't even need to be given this information to answer the question. That's irrelevant. What we need to look at is what delta S represents. Delta S deals with entropy, which deals with order. Is this system getting more ordered or more disordered? Okay, so when we look at it, we have 2 particles here plus 1. That means we're going from 3 to 2. 3 to 2 particles. What is the sign on delta S? Negative. There's only one answer with a negative value. This question is brilliant. I hope you see a question like this on the AP exam. You do not need a calculator for this. This is a concept question. Number 19. The reaction where we have 4 silver atoms plus oxygen yields silver oxide. And it's exothermic. Alright, what statement about the reaction is correct? It is spontaneous at all temperatures. Well, let's see. We have a delta F. Well, we have, okay, here's what we have. Delta H is negative. Delta S goes from 5 particles to 2, so negative. So absolutely not. The only way that this is going to be spontaneous where we have delta G being negative is at low temperatures, period. So, A is out. Looking good. No. It's spontaneous at all temperatures. It's non-spontaneous. No, it's spontaneous at some. And at low pressures is garbage. So B. Okay. Know the scenario with H, S, and delta G. Please. You're going to see questions like this. Number 20. What is the total number of valence electrons in the thiosulfate ion? Well, remember when we talk about valence electrons, we want to know, okay, well, what group is it in? So sulfur, since it's in group 6, we have 1, 2, 3, 4, 5, 6 valence electrons. Okay, so each sulfur brings with it 6 electrons. So we have 6 electrons times 2. Oxygen, same column, just above the sulfur, 6 electrons. We have 3 of those. Now here's the kicker, that negative 2. those are valence electrons that were given to this nonmetal by some metal. Okay, they were given to the nonmetal by some metal. So we have to add those in as well. So we have 6 times 5, which is 30, plus 2, 32. Letter C. Alright. I hope this wasn't too daunting of a task for you. There were a couple interesting questions on here. And you're going to have some very interesting questions on the AP exam. So again, I hope this video has helped, and hopefully this wasn't the last video for you to attempt.